client in the encrypted space. And then the client encrypts its data, sends it to the server, and then the server can run the neural network without seeing any input or output. And then he sends back the output, and the client can decrypt it. So the main problem with fully homomorphic encryption, you may have heard of it, it's the performances. So this step is very, very slow. We are talking about 3 or 4 orders of magnitude slower than the regular computation. But there's a second problem, which is the ciphertext expansion, which is that when you encrypt your data, you get ciphertexts that are about 200 times larger than the original data. So it's going to be a pain to send to the server. But there's a solution that is known for a long time, which is called transciphering. And the point of transciphering is to encrypt the data not directly with the homomorphic scheme, but with some sort of with a symmetric cipher, something more classical. So you don't have any ciphertext expansion. And then you take the key of the symmetric cipher and you encrypt it homomorphically. And then you send that to the server. And once you have that, the server, he wants to recover the data in the homomorphic form to be able to do his job. And so what he's going to do is to take the decryption algorithm of the symmetric cipher and run it homomorphically. And if you do that, you have my word that you recover the data on a homomorphic form. So now the ciphertext expansion problem is solved because you don't you just have to send the data, the key, but it's going to be quickly amortized when you send a large amount of data. But now you have a new problem, which is that this is very slow, and so you need to pick the right scheme, the right symmetric scheme, to so that everything works fast. And the thing is, you cannot use standard ciphers. Like, for example, you cannot use AES because all the classical ciphers that we know in the literature, they have not been intended to do that. And so you need to design new ciphers that are going to be efficient in this for this particular use case. Okay. And so, yeah, you may have noticed that we have a lot of authors. It's because in the team there are a subset of people that are very, very good at designing symmetric algorithm and doing cryptanalysis and so on, and a subset that is interested in designing efficient homomorphic applications. And so with Transistor, we hope to get the best of both worlds. Okay, so now I'm going to spend a bit of time to introduce you to TFHE. So TFHE is the homomorphic scheme that we target with transistors. So how it's working? Very quickly. So the message you encrypt, the plain text space, is a small ring. So by small I mean P has a few bits, so no more than 8 bits. Then so the secret key, it's a vector of bits, and when you want to encrypt a message, you embed your message in a larger ring. So that Q here, so Q is usually 2 to the 64. And then you sample a random mask of elements of this ring, you compute the inner product, you add the message that you have moved to the most significant bits, and finally you add a small random Gaussian noise, and just like that you build learning with error instance. So this is a quite basic lattice-based encryption. But what's really interesting with TFHE, of course, it's the homomorphism. So what kind of homomorphism do we have? We have linear homomorphism. So so you can add 2 ciphertexts, you can multiply ciphertext by a constant. All these operations are very fast. They are quite conceptually very simple. The thing is, as you have encrypted with noise, when you are doing math with noisy values, you recover results that are even more noisy. So you cannot do linear homomorphism forever, because at some point, the noise is going to be so large that you're going to destroy the message the information you have in your ciphertext. But there's a way out of here, which is the programmable bootstrapping. So the PBS. So the PBS, it's kind of the killer feature of TFHE. So it's an operation that does two things. So first, it resets the noise to a nominal level, which means that if you did too much linear operation and you have a lot of noise, you can just run the bootstrapping and recover a clean ciphertext and keep going with your computation. And what's interesting is the word programmable. It means that while you are resetting the noise, you can evaluate a lookup table on the message. And so basically, you have your noisy message here, you run a PBS, and then you get a noise-free, like there's still a bit of noise, but a noise-free message that encrypts f(x). And there's one other thing I want you to know about TFHE. It's something called the negacyclicity problem. And without entering into the details, it means that if you take a plaintext modulus that is even, you're going to have some restrictions on the functions that you can evaluate with this PBS. So there's countermeasures, but they make the design of homomorphic circuits quite difficult. And this problem disappears when P is odd. So that's why we made this design choice. So now that we are all set with TFHE, we're going to think about what does an ideal symmetric cipher would look like for TFHE. So first, you want, as I said, a small prime field because of this problem that I just mentioned. You want to have as little nonlinear operation as possible because the only way to do nonlinear operations with TFHE is to run the bootstrapping, and bootstrapping are very slow. And finally, you want controlled noise growth because if you do not have a mechanism in your circuit to regulate the noise, it's going to blow up and you're going to decrypt the wrong message. Okay. So with that in mind, we can move to the actual specification of transistor. So transistor, it looks like this. So I'm going to go through its different components. So you may notice that we are working in F17. So I'm going to elaborate on that later. And how does it work? So you have a state here that is looping on itself. And the state, it's a square grid of F17 elements. And it gets through a kind of AES-like transformations, so a bit like in Lex, if you're familiar with it. So you have a layer of S boxes, a shift rows, a mixed column. And so, and then the key is introduced at this point where you have a feedback register, so an LFSR, that generates round keys and that gets some absorbed in the state. And at each clock cycle, we filter out 4 elements of the state. We add a bit of whitening here, and this gives us our key stream. So that's the layout of it. So if we come back to our wish list, so we wanted a small prime field of our characteristic. So the contract is honored. So we have we are working on F17. So 17 is the next number because the bootstrapping is very efficient. It's small enough, so the bootstrapping is very efficient, and it's a power of 2 plus 1. So it's handy to just pack a nibble of 4 bits into an element of the field. And the consequence of that is that here we have 2 plus operations, and those are actual plus of TFHE. So they are costing basically nothing. And it wouldn't have been possible to do that if we would have, like, for example, a power of 2 here. So that's the thing. Then we wanted as little non-linear operation as possible. And well, the only nonlinear operation in the whole scheme, it's this layer of S boxes here. So that plays two roles. First, it's evaluating the S box, the function of the S box, so to introduce security of the scheme. And also, it's reset the noise. So the noise is not accumulating over time within the state. So over time, the noise in output here is a constant. But I'll come back to that later. And finally, we want so a mechanism of control noise growth. So I already talked about the S box, but there are two other places where the noise can blow up. So the first one is here in the mixed column. So basically, we are multiplying the state with a clear matrix. And the thing is, multiplying by a constant makes the noise increase. But we managed to find a matrix, so this matrix here, so that has two main properties. So first, it's MDS, so it has all the nice properties of optimal diffusion to make proof. And also, the thing is, the noise increase that it's going to occur, it's proportional to the norm of the rows. And so we managed to find this matrix that is the MDS matrix with the smallest norm on its rows. So that's quite nice. And then the other spot where noise can accumulate, it's of course the LFSR. So if you think about it, if you want to implement LFSR, what you do is that you have like a register and you feed it with the seed. And then at each clock cycle, you compute the new element of the register by computing a linear combination between the content of the register and your coefficients, your retraction coefficient. The thing is that if you do that with TFHE, the noise is going to increase over time. And so at some point, you will need some bootstrapping and so on. But what you can do instead, it's to take kind of the dual approach of saying, well, everything is linear, so at any point of time, I can compute a linear combination that is going to yield the output with respect to the initial input. And so what we do is that at each log cycle, we compute this linear combination instead of computing a new state. And so the consequence of that is that the output of the LFSR, so of this kind of noiseless LFSR, it remains stable over time and it doesn't use any PBS. So that's great for performances. Okay, so I'm going to go a bit quickly on this. So just to talk a bit about noise management, so I indicated here on the drawing the indicative noise level with these gauges. And the critical point is here because it's right before the bootstrapping. And so it's at this point you have too much noise, the lookup table is going to yield the wrong value and it's going to break everything. But thankfully, we have like some guarantees that the noise here will be bounded with some probabilities. And so, and the good news is that so the noise here is the sum of the noise here and the noise here. And as you can see, the noise here is mechanically much higher than this one. So we can take an LFSR here as big as we want, and it's never going to be a problem. So that was great for the designers. Okay, I'm going to go fast on this. And then I'm going to finish with some cryptanalysis. So is transistor a secure cipher? Because that's the entire point. So the first thing we looked at, it's of course time memory data trade-offs. So if we pick these dimensions for the LFSR, so 64 elements of the field for the key schedule and 32 for the whitening. And if you do the math, it ensures a limit on the key streams of 2 to the 31 digits with a single key. And of course, if you are in a multi-IV setting, you can push it much further. And for guess and determined, the thing is, so if you look at the filtering procedure, it's clear that an attacker would have to guess 3 out of 4 elements of the state, and he would have to guess the entire whitening LFSR. And so if you run the numbers, it's it's quite a massive entropy. And also, we looked at correlation attacks. So the point of correlation attacks is to try to build correlation between the content of the key LFSR and the output key stream. And we have a proof that proves that 3 consecutive outputs of a transistor are statistically independent from the secret key, which means that if you want to mount a correlation attack, you would have to take at least 4 elements. And if you run the numbers, you understand that the value of this correlation is actually pretty low, and the conclusion of that is that if you want to launch a correlation attack, you require at least 2 to the 41 digits, and so this bound already exceeds the bound, the kind of trivial bound enforced by the time memory data trade-offs. So we are safe from here. And by the way, this is without taking into account widening. So I don't have time for this, but there's more cryptanalysis in the paper, so linear distinguishers and algebraic attacks. And very quickly, just talking about performances. So we compare transistor to the other TFHE-friendly cipher of the literature. So there's a lot to unpack here, but the main point of transistor is that you don't have any setup time, and we have a pretty good communication cost because we don't have a lot of noise increase, and so we can take very tight parameters, very small parameters for the TFHE scheme. And so we have very small evaluation key, and the key of transistor itself is also quite small. And we dimension it to guarantee a very, very, very small error probability. So we have kind of a good metrics on good performances on all of these metrics. Yeah, so thank you very much. And, I'm happy to take questions.
So questions. So I have one question. So when you were talking about the noise controlling in LFSR, that was symbolic execution. That's the idea of trying to make sure you don't do all the additions right at that moment. So what was the trick?
The trick is that instead of at each clock cycle computing the same linear combination to get the next element in a kind of iterative way, what you do is that instead you compute the coefficients of the linear combination themselves. So you kind of square the polynomial. To get the second element, you kind of square the polynomial, the retroaction polynomial, then compute the linear combination, and so on and so on. And so computing these coefficients can be done in the clear. So it's not a problem.
Okay, great. Thank you. If there are no other questions, then let's just thank the speaker again. The next talk of the session is it's a Zoom talk. So as I believe all of us know, that we won't be able to ask questions, but please email the authors if you want to ask questions about this talk. So I think we're going to watch a recording now.
Hi everyone.
So the next
I am
talk is on
Abhishankar Saha.
tweakable permutation-based Blueberry rack of constructions, and the talks by Biswajit Chakraborty and Abhishankar Saha.
Hi everyone. I am Abhishankar Saha, and I am going to present our work, tweakable permutation-based Blueberry rack of constructions. This is a joint work with Biswajit Chakraborty. So let me first introduce the Blueberry rack of construction. As you might all know, it is a mode to convert an n-bit to n-bit function to a 2n-bit permutation as depicted in the image. And this can be extended to r rounds by taking r n-bit functions, f1 to fr, and you compose the Lubidakov transforms of these FIs one after another to get the R round Lubidakov construction depicted in this image. Now, in most security proofs regarding LR construction, they are done in the heuristic of the random oracle model, where you bound the PRP security of the LR construction by the PRP security of the LR construction instantiated with independent uniformly random functions as the internal primitives, plus the PRF advantages of the original primitives FIs. But in most practical cases, these internal primitives are instantiated by block ciphers, and then we are stuck with the birthday bound because of the PRP-PRF switching lemma, which says that you can distinguish between a PRP and a PRF using only 2 to the power of n by 2 queries, and hence this term, this PRF advantage of the block ciphers, gives you the birthday bound. So if the internal primitives are instantiated by block ciphers, then it's better to analyze the security of the Lubidakov construction when the internal primitives are actually permutations and not functions. And this is called the permutation-based Lubidakov, or in short, PLR. Now, the only existing beyond birthday bound analysis of the PLR is given by Go et al., who showed that 5 rounds of PLR achieves 2n by 3 bit security, 2n by 3 bit CPA security, where you can query the construction in the forward direction, and 7 rounds of PLR achieves 2n by 3 bit CCA security, where you can query the construction both in the forward and the inverse direction. Now we come to the question of tweaking the Lubidakov construction, and this was first done by Goldenberg et al., who showed that for single block tweaks, if you take 7 rounds of LR, this is LR, not PLR, this is function based. So if you take 7 rounds of LR and inject the tweak in the 3rd round, then you get an n-bit CPA secure tweakable pseudorandom permutation. This is optimally secure. And also you get an optimally secure tweakable strong pseudorandom permutation if you take 10 rounds of LR and tweak and inject the single block tweaks in the 3rd and the 8th round. Also, for general length twins, suppose there are T blocks of tweaks, then they showed that this construction achieves optimal CPA security. Of course, as you can see, it contains T plus 6 LR rounds, and this can be seen modularly as so the left part of the construction, the left to the gray line, can be seen as the tweak processing part, which contains T plus 2 LR rounds, and it processes the tweak, and then 4 more rounds of LR are added to it to give you the entire construction. So this is a CPA secure candidate proposed by Goldenberg, and for CCA security, they just apply the tweak processing part symmetrically on the other side of the 4LR2. So this is 4LR sandwiched by the 2 tweak processing parts, both of which contains T plus 2 rounds, and in total then it is 2T plus 8 rounds for CCA security. So these are the candidates of Goldenberg et al. Now, now we come to our contributions. So first we give the 2 motivating questions of this work. So the first question was whether the results of Goldenberg et al. Can be extended to PLR constructions. So whether the functions in the Goldenberg et al. Construction be replaced by permutations, and also the number of rounds in the tweak processing part of the Goldenberg candidates is quite large. It's T plus 2 LR rounds, which is quite expensive. So we investigate whether such number of rounds can be reduced when we consider permutation-based LR. So to just replace the functions in the Goldenberg candidates with permutations, we get these constructions. But for CCA security, we consider one more round of PLR. So instead of 4 round PLR being sandwiched by tweak processing parts, we actually consider 5 rounds of PLR sandwiched by the tweak processing parts. So now our first contribution is to define the TLR compatible function family, which is to formalize the exact probabilistic requirements from the 2n-bit to 2n-bit tweak processing maps, so that these constructions respectively achieve n-bit CPA and CCA security. And so we define the TLR compatible function family as follows. So a TLR compatible function family is a family of tweakable 2n-bit to 2n-bit permutations with T blocks of tweaks, where for any distinct inputs, the probability of full collision of the outputs is bounded by 4 by 2 to the power of 2n, and the probability of collision in the right half of the output is bounded by 2 to the power of 2n. And we instantiate, so this is the TLR compatible family definition that you need the tweak processing maps to follow, so that the candidates presented in the slide before achieves optimal CPA and CCA security respectively. And we instantiate these TLR compatible families using one round of PLR as follows. So for single block tweaks, we pass it through a uniformly chosen random permutation and XOR it to both the wires of the PLR. And for general length tweaks, we pass it through two AXU hash functions, rho1 and rho2, and then XOR it to both the input and output wires of the one round PLR. So these are our instantiations of TLR compatible family. And then just substituting this in the constructions, in the modular constructions we have shown before, we get the following candidates. So this is the single block tweak candidates. This TLR P5 achieves optimal CPA security as we have shown, and this TLR P7 achieves optimal CCA security. Similarly, for general block tweaks, we have this TLR P5 plus construction, where these are AXU hash functions. Similarly, TLR P7 plus achieves optimal CCA security. So these are the four of our candidates. And now we give a brief description of the proof of, and for example, we take TLR P5 to give the proof sketch to give you a hint of the combinatorial contribution of this paper. So this is the modular TLR P5 construction, and the transcript is this. This tweak, the input, the 2n-bit input LIRI and the 2n-bit output SITI, and we prove this security using the H coefficient technique, where the general strategy is to define some bad transcripts which are very low probability in the ideal world, and we also need to find the ratio to lower bound the ratio of the probability of attaining the transcript in the real world is to the probability of attaining the transcript in the ideal world. So in our proof, we actually considered the extended transcript, where we uniformly sample F from the TLR compatible function family as we have defined above, and we also sample uniformly sample a permutation pi from all n-bit permutations, and we compute this Li prime and Ri prime, and these are adjugated to the actual transcript. So this is our extended transcript, and now you can see that the probability that this extended transcript is realized in the ideal world is basically the probability that the 3-round PLR instantiated with pi 1, pi 2, pi 3 outputs SITI on input Li prime, Ri prime, where the probability is over the random choices of pi 1, pi 2, pi 3. So basically, we have to calculate the number of permutation triples pi 1, pi 2, pi 3 such that the output of the 3-round PLR is SITI when input with Li prime, Ri prime. And so what are the unknowns here? So we know that the input of the pi 1 is just Ri prime. The output of pi 2 is Ri prime plus SI. The input of pi 3 is just SI. And the unknowns are basically the output of pi 1, which we denote by Xi, the input of pi 2, which we denote by Yi, and the output of pi 3, which we denote by Zi. And if this extended transcript has to be compatible with the real world construction, then these unknown variables must satisfy this system of linear equations. And this is true for all I belongs to Q for Q many queries. Also, the permutation properties of pi1, pi2, pi3 imposes some set of equalities and non-equalities over the unknowns, which is basically that if pi is a permutation, then its outputs will be distinct if and only if its inputs are distinct. So from the permutation property of pi1, we have that xi is equals to xj if and only if we have that in the extended transcript ri prime equals to rj prime, and similarly zi equals to zj from the permutation property of pi3 if and only if si equals to sj in the extended transcript, and similarly this comes from the permutation property of pi2. So these are the set of equalities and non-equalities. So these are also non-equalities, because if ri prime not equals to rj prime in the extended transcript, then we must have xi not equals to xj and so on. And this set of the system of equations and the set of equalities and non-equalities can be succinctly represented in graph theoretic terms as follows. So if you consider a graph with vertices being the unknown variables, and there is an equation between two vertices only if there is an edge between two vertices only if there is an equation between the corresponding variables in the system of equations, and the constant of the corresponding equation is given as the label of that edge. So that is the labeled undirected graph you get from this system of equations. And now whenever there is an equality, there is an identical equality imposed by the transcript, we merge those two vertices. So if the transcript imposes this equality xi equals to xj, then we merge the ith x vertex and the jth x vertex. So finally, after this merging, we get a graph like this. So like in this example, in this image, you can see that following equalities were imposed by, so the system of equations are basically this x1 plus y1 equals to L1 prime, this y1 plus z1 equals to t1 and so on. While the equalities imposed by the extended transcript are, as you can see, is y1 equals to y2, x2 equals to x3 equals to x4, z3 equals to z5, z6 equals to z7, and y7 equals to y8. So these are the graphs you get representing the extended transcript. And now we define the bad transcripts as those which result in graphs that contains cycles or has a component of too large size, or has a path between two x vertices or two y vertices or two z vertices of level sum 0, because these conditions somehow result in inconsistent solutions. So inconsistent system of equation which has no solutions respecting the permutation property of pi1, pi2, pi3. And all these bad events can be bounded by to the order of q by 2 to the power of n due to the TLR compatibility of the tweak processing part. And this is exactly where we need the TLR compatibility criteria. Now, as you can see, the number of XYZ respecting solutions, where by XYZ respecting solutions, we mean that X being the partition of the X vertices, Y being the partition containing the Y vertices, Z being the partition containing the Z vertices. What we need from our solutions to the system of equations is that distinct X vertices must not be assigned the same value. Similarly, distinct Y vertices must not be assigned the same value, and these distinct Z vertices must not be assigned the same value. There might be overlap between the values assigned between assigned to some Y variable and some Z variable, that we don't care about that. But distinct Y variables, distinct vertices belonging to the same partition must not be assigned the same value. And we see that the number of XYZ respecting solutions is exactly equal to the number of permutation triples, such that the 3-round PLR with pi1, pi2, pi3 as the internal in primitives gives the output SITI on being input Li prime, Ri prime, which is exactly what we needed for the edge coefficient analysis. And this is where mirror theory comes up. This is the main combinatorial result which we proved in this paper, which says that if you have a system of equations, system of E equations on Q variables, and the variables are partitioned as V1, V2, V3, and the largest component size is xi, where xi is bounded as follows, and the number of variables is bounded as this. then the number of V1, V2, V3 respecting solutions is basically lower bounded by this quantity. And this quantity is motivated by actually the number of expected V1, V2, V3 respecting solutions of the system of equations when the constants of the equations in the system are chosen uniformly randomly. And as a consequence, we have that. So this we have the security of PLR. If we ignore the tweak processing parts of our tweakable permutation candidates TLRP5 and TLRP7, then we see that the 5 rounds of PLR is actually n-bit secure PRP, and the 7 rounds of PLR is n-bit secure SPRP, which is quite an improvement over Guo et al.'s results, who only showed 2n/3-bit security for these constructions. Finally, we give some future directions to our work. One is minimizing the number of block cipher calls for attaining optimal security. Secondly, we can instantiate the secret block ciphers for the internal primitives by public permutation-based key alternating ciphers. Thirdly, we can consider single key versions of our candidates, as we have seen that each of our candidates, so each of the rounds of our PLR constructions used independently keyed block ciphers, and rekeying is expensive, so single key version need to be considered. And optimizing TLR compatible families. So these are the constructions we have given, while some reviewer have suggested some optimized versions of these constructions. So there is another future direction. Finally, I would invite you to look into our ePrint paper, because it has some additional results about optimally secure MAC constructions. And that's all. Thank you.